spin, let's say, so your spin values are either plus or minus a half. Okay, so your J now here will be either, for a given L, will be either L plus a half or L minus a half. Because we're assuming spin values a half, right? Now, if L's naught, this is naught, but if L is non-zero, positive, then the energies with the spin orbit switched off, hypothetically, right? The difference, like if you plug in J is L plus a half, and these S's will just be a half, right? And you'll get two values, right? Because they're just two values of J, this and this. So the difference between those two values, the different energies, call that delta E. Now this here is just the energy you add, for given J, L and S. That's the energy correction to your Hamiltonian, the eigenvalue. But for the two different values of J, you get two different energies, and the difference between those two energies is this delta. Well, they're both deltas. This is a big capital delta. This is a small delta. Okay, so the difference between those two, when you plug in J as L plus a half here, and plug in L minus half for J here, the difference between those two energy values works out to be this, right? And so the upper value for this will be this times 1 over 2L plus 1. So that's the lower shift. It'll shift down by this amount. Okay. And for the upper one, when you use this one, the upper shift is this much, and the lower shift will be this much multiplied by this factor. So what I'm trying to say is that because of the spin orbit effect, the allowed energy levels, just N or NL, they will be split. Instead of being just one energy level at a given N, and little n and L, now there's two. Right? So they'll shift up and shift down. Now in the next session I'll draw some pretty pictures, diagrams, so you'll see these shifts. Now they're small, right? They're small shifts in energies, and that's a consequence of the alpha. You can see it here. This alpha fourth power here. Now alpha, the fine structure constant, it's already 1 over 137, right? So you take that to the fourth power. Well, let's approximate. What is that? It's very small. What is it? This is roughly 1 over 100 to the fourth power. That's 1 over 10 to the 8. That's 100 million, right? So it's a very small effect, but hence fine structure. Okay, now this spin orbit phenomenon is not the only phenomenon that gives you this energy change that's proportional to the fourth power of the fine structure constant, proportional to alpha to the fourth. Now I just put it here as a bit of a joke because you've got alpha fourth. Okay, so there's another phenomenon besides spin orbit that gives you this energy change that's proportional to a to the fourth, a very small correction, and it's a relativistic phenomena. So don't worry about it too much because we need to do Dirac's theory. But yeah, we'll come on to it later. Let's see, what's a consequence of? The kinetic energy term gets changed, right? And it's a relativistic correction that comes out of wedding the theory of relativity, special relativity, to quantum mechanics. In other words, it's a consequence of Dirac's work. Okay. Now, when you put these two phenomena together, this kinetic energy change due to relativistic effect in Dirac's theory, and the spin orbit coupling, you put those two together. So now you'll add two terms, two corrective terms, two perturbations to your Hamiltonian. Then some other odd stuff comes out. For a start, the energy shift formula is this. You get this. And this is what I mean when I was starting this session, saying quite a few details. You may find them interesting or not. So when you add those two perturbations to the Hamiltonian, the change, the shift in the energy eigenvalues is of this order. Okay? And here is the energy quantum number, which discrete energy level are you talking about, say for hydrogen. And here again, here's your alpha to the fourth again. This is the energy change for when you have the two phenomena, two corrections, two perturbations in your Hamiltonian. Okay. Now, certain odd things happen. Often the devil is in the details. Often new phenomena in physics get discovered when you look at the really fine stuff. That's often how you find new physics. Now, curiously here, for when L is 3, and for two values of J when they're 5 over 2 and 7 over 2. Now J, let's see. Now we can figure that out immediately. Like if L is 3, right, that's one of the discrete quantized values of the angular momentum. So if it's 3, and the S values are half, so it can be either parallel or anti-parallel. So your J, which is L plus S, let's say, because it's spin orbit interaction. So your J will be L plus a half or L minus a half. Well, there's minus a half, there's plus a half. So 2.5, 3.5. Okay. Now for those two values of J, you plug them in here for certain n. Then this split, this change in the energy value here, works out to be the same for two different cases. One is if you calculated the split orbit alone, if you did not include the relativistic change. Now, exclamation mark. This is puzzling. There's still open questions in physics. Right now, a few more little details. So for the special case when L is 0, that means there's only one value of J because it's a half. So if L is 0, think of J as L plus S. Well, L is 0, so it just leaves S. So J is a half. Okay. Then this equation here. So if J is just a half, no split. So this should be 0. Does that make sense? That doesn't seem to make a lot of sense to me. Anyway, that's what the textbook says. So this the correction here just becomes 0, just under these circumstances, special circumstances, when L is 0. Now, just to finish off this section, in the next session, I'll give you some diagrams, and which map the energy. They indicate the energy levels for different values of n. So in this case, for n is 4, so it's the fourth allowed energy level in the hydrogen atom, and for various values of L. So if you're plugging in n and L into, so now this is your general formula that resulted from 2 alpha to the 4th power effects, spin orbit, and the relativistic correction on kinetic energy. Okay, here. So if you know n, so here and here, you know L. So this is for J. So So is it ignoring spin? Not too sure about that. Anyway, the point is, these figures will show you the corrections in the energy levels due to these effects, and they're small. They're like the energy differences between the allowed allowed energy levels of the hydrogen atom, the energy quantum number n, little n is 1, 2, 3, 4. The differences in the energies of those is of the order proportional to alpha squared. Okay? This is proportional to alpha squared, fine structure constant squared. Whereas these corrections, the two I've been talking about, they're proportional to alpha to the fourth power. So they are, let's see, so they differ by a factor of alpha squared. Alpha's 1 over 137 roughly. So we're talking a change of one part in about 10,000. Okay, so in terms of the difference in energy levels between n is, well, say n is 3, n is 4, n is 5. So it's of that order, about one part in 10,000. So small corrections. But the fact that theoretical physics, quantum mechanics, can actually have a theory about such fine levels of detail, and that theory matches very well, very closely, to experimentally observed, finely measured phenomena, is really quite remarkable. Einstein himself, he said for him, the greatest mystery of existence was the fact that nature was comprehensible. What is it about nature that allows human beings with our brains, human brains, to understand the phenomena of nature with such incredible mathematical accuracy? It's a deep metaphysical mystery, right?